Hello. I think we're already past the hour, so I will start. My name is Roger Pau, and I work at Citrix on open source Zen. My previous work on Zen has involved PVH, the PV shim, and miscellaneous bits on the hypervisor. And I've been also working on other related projects like EMU or the Linux kernel, and I also attempt to maintain and improve the Zen support on FreeBSD. And I'm here today to present some tentative work I've been doing to fix issues I found related to virtual periodic timers used by x86 HVM guests. Note that this subsystem is only used for emulated timers. The PV timer don't use this at all. So the topic is quite specific and also quite technical, so I've attempted to make the talk not go very deeply into the code details. So I hope people not very familiar with the topic will be able to follow the talk and understand the motivation and the results of the work. This is also still pending review on the mailing list, so some of the patches or some of the preliminary patches have been accepted, but there's still quite a lot of work left to be committed in order for it to be done and fixed. So let's just start by explaining what are virtual timers and how they are used by Zen. The main aim is to provide a set of helpers in order to simplify managing timer-related interrupts for HVM emulated devices. So the emulated device provides a timeout and the interrupt injection details, for example, whether it's a local APIC or an IO APIC triggered interrupt, and optionally a callback to be executed when the timer expires. Then the framework takes care of injecting the interrupts on behalf of the emulated device in a periodic way, if told so. It also deals with the timer modes that can be selected by the user, whether time counters should be delayed for missed ticks, and whether missed ticks accumulate instead of being dropped if it cannot be delivered because the guest is not currently running, for example. Such modes are important for some guest OSs. For example, some versions of Windows use the timer interrupts in order to keep track of time. So if you miss interrupts and you skip them or you accumulate them, that prevents the clock from advancing and creates a time skew inside of Windows. By having all the logic abstracted in a single place, we can avoid having to add quite a lot of code to each emulated device. So in that sense, it simplifies the implementation of emulated timer devices for HVM guests. Internally, the logic to deal with virtual timers is not very complicated from a high-level point of view. A callback function is registered with the generic hypervisor timer subsystem and set to fire after a given offset. When that callback is executed, note that this is an internal callback, not the one the user provided. The virtual timer is marked as having a pending interrupt to be delivered to the guest. Then, just before the guest resumes execution, Zen will check whether there's a timer interrupt pending that can be injected. This doesn't seem very complex, but there are issues with this approach that prevent virtual timers from working properly in all scenarios. Let's look at some of them. First of all, timers are currently tied to a specific vCPU set by the caller, which is usually the E8259 target. That's the legacy programmable interrupt controller, the legacy PIC, or vCPU 0. That's the target that's usually tied to the virtual timer. Note that this vCPU is set independently of the target of the timer interrupt. For example, a caller could bind a virtual timer to vCPU 0 and then have the interrupt generated from that timer be delivered to vCPU 2, just adjusting the routing of the interrupt source on the interrupt controller. An IO APIC pin, for instance. This can be done without modifying the virtual timer at all. So the virtual timer is not aware that the target vCPU has been changed, and also the virtual timer is still bound to the same vCPU. So this sadly doesn't work properly because the target of the generated interrupt needs to be the same as the vCPU tied to the virtual timer, or else the logic in the resume to guest path doesn't work properly. In case of a mismatch between the target of the interrupt and the vCPU the timer is tied to, the logic that checks whether a timer interrupt has been injected will never return success, as the interrupt has been injected to a different vCPU, and hence further virtual timer interrupts will get stuck, waiting for confirmation that the currently pending one has been injected. Such logic to check whether a timer interrupt has been injected is also quite cumbersome, since it's executed on every return to guest, which is a very performance-sensitive path that should be as fast as possible. So in that sense, trying to remove the logic should also be good from a performance point of view. Finally, there's also some complex locking discipline to protect virtual timers while also attempting to not introduce a lot of contention. Virtual timers are generally protected by a lock from the vCPU they are assigned to. This causes quite a lot of complexity and corner cases when timers are migrated between vCPUs. For example, XSA336 was a result of incorrect locking when migrating a virtual timer between vCPUs. When attempting to fix the issues detected, there are several constraints that have to be taken into account. First, there's the logic with accumulating missed ticks, which is quite complex. We need to check whether the interrupt source is masked and if the interrupt can be injected. It also seems like the currently implemented logic to accumulate in mistakes when the source is masked is wrong, since it should only accumulate mistakes when the guest is preempted. In any case, a fixed version of the mistakes logic needs to be preserved in order to not break OSs that rely on it. Another important point to take into account is that timers for guests that are preempted shouldn't be kept running, or else a guest setting a high-frequency timer could cause other guests or the host itself to be interrupted in order to handle the processing of the ticks from the preempted guest. So the proposed solution is slightly different from the current approach, which could be seen in a way similar to polling. On every guest resume, Zen checks if the conditions allowed for a timer interrupt to be injected. The new logic, instead of relying on this kind of polling, attempts to use an event-driven mechanism. The proposal is to trap end of interrupts performed by the guest and use that in order to detect when a virtual timer interrupt has been processed by the guest. Trapping end of interrupts is already being used by Zen for PCI pass-through, so there's already code that handles this. It's also less intrusive than the current approach, since it doesn't require adding more code to the resume path and works correctly even if the interrupt target vCPU diverges from the timer assigned vCPU. As part of the work to fix the timers, I've also attempted to provide a more generic framework to register callbacks to be executed when end of interrupts are performed. Such framework should be used both by the pass-through code and also by virtual periodic timers. So albeit we can get rid of the code executed on guest resume, we still need to keep the logic to detect if an interrupt source is masked, or else edge trigger interrupts could block indefinitely waiting for an end of interrupt event. as an edge trigger interrupt that's injected while the source is masked will just be dropped. Apart from being able to remove the guest resume path logic, this approach has also led to quite a lot of code removal in the virtual timers interrupt logic itself. So I think it's easier if we see a diagram of what I'm proposing to do. This is a graphical representation of the current and the proposed models. Let's look at the diagram at the top, which contains the current flow. The diagram represents the code execution of a physical CPU over a certain period of time. Note that the time used by Zen and the guest is not proportional to what we would usually see on a real execution trace. It's just something to make it easier to display. So let's start by the current approach. While the guest is executing, we can see that the virtual timer expires and the context is switched to Zen. At that point, Zen marks the timer as having an interrupt pending, and maybe we'll also do other stuff that's up to Zen. And then just before resuming guest execution, Zen will check if there are any pending interrupts to be injected and if they can be serviced by the guest. For example, the guest could have higher priority interrupts that are also pending, or could have interrupts disabled, for example. So here, let's assume that the guest has interrupts blocked at this point. So we are not injecting the timer interrupt here. Then the VM resumes execution, and at some point we get another context switch to Zen, in this case because the guest has enabled interrupts. So when we try to resume guest execution, in that case, we can inject the pending timer interrupt that we had. When we do that, Zen also runs the logic to account for misticks, and we also rearm the virtual timer if required. So if there are no other ticks to be injected, we will set a new timer interrupt in the future in order to continue injecting. The diagram in the bottom, on the other hand, would be what I'm proposing, the new proposed flow. The first part is exactly the same. The guest is running and a virtual timer expires. Context is switched to Zen, and at that point, the interrupt is injected to the guest using the selected source. In that case, this means setting the interrupt as pending on the interrupt controller, usually the IO APIC or the local APIC. Note that in this case, the interrupt is just set as pending on the interrupt controller, and there's no longer any kind of polling to check whether the guest is ready to service it or not. Then we will continue execution as normal. We may get other exits from the guest into Zen, and at some point when the guest executes the end of interrupt, we'll get a trap into Zen. At that point, we know that the guest has serviced the interrupt, and we can run the logic to account for mistakes, and we can also rearm the timer if there are no mistakes to be delivered afterwards. So I've got a question from Edwin. I think we can take it because I'm almost done regarding a slide, so I don't mind replying it now. What happens if a timer expires while the guest is running? Will that trigger a transition to Zen, which could then immediately deliver it to the guest if end of interrupt was already run on previous timer interrupt and just accumulate otherwise? Yes, so if you get... does that refer to the current logic or the previous logic that we had? Yeah, I mean, if you get a timer that expires and the guest is running, it will trigger a transition into Zen, and then we would immediately deliver to the guest. Yeah, that's exactly it. And I mean, the thing is that you cannot get a timer interrupt if the guest hasn't executed an end of interrupt before, because we only rearm the timer after the guest has executed an end of interrupt. So there should be no time when a virtual timer expires while you still have a pending end of interrupt to be delivered, because we won't have rearmed the timer. So even if the virtual interrupt is set as periodic, we will only rearm the timer once we get the end of interrupt from the guest. So we are not running. So we don't have a timer set unless we are ready to inject one to the guest, basically.
And as I understand it, also unless there is an immediate need for another interrupt injection.
Yeah, well, yeah, of course. If there's no need for injection, then of course we won't be set.
With the mystics accounting, this can quite easily happen.
Yeah, exactly. With mystics, as Jan said, when the guest does the end of interrupt, we may already have mystics pending to be delivered. So in that case, what would happen here is that the guest does an end of interrupt, and we then inject another interrupt straight away without rearming the virtual timer, because the guest has already accumulated pending interrupts to be injected. So yeah, there are still some comments that need to be fixed in the current patch series. One of them is making the callbacks that can be executed for end of interrupts fixed, so that we don't introduce indirect jumps in a performance critical path, which would be the end of interrupt. Another issue is that mask interrupts are accounted as missed ticks now, which is an error in the current code as far as I know, and something that Jan pointed out during the review, which according to the documentation, missed ticks should only be accounted for the period of the time that the guest is preempted, but not when interrupts are explicitly masked. So right now we are accumulating pending interrupts when the guest has masked the interrupt source, but that shouldn't be the case. Those should be dropped. And one pending point that needs to be solved is what to do with the RTC strict mode. Zen has been setting the RTC good flag in the Windows ACPI emulated device table unconditionally. So the RTC doesn't require the guest to perform a rexy read in order to inject further interrupts. I've made a proposal to fully remove such mode because it interacts badly with the new logic to manage virtual timers, but there's still some controversy over whether we should keep it. Note that there's no option for users to select this mode, so it can only be selected by modifying the source code and rebuilding Zen. And then I think I still have some cleanup of the patches to do. So yeah, the main aim was to fix the delivery of interrupts so that it works in all possible scenarios. This, however, has led to, let's say, a major rework of the current virtual timers logic. And I think that such new logic should help remove some of the overhead from the VM entry path for HVM x86 guest, and also simplify the code used to manage virtual timers, which is quite complex now. It's still quite a lot of, well, it's still a work in progress. I think, well, some of the patches have already been reviewed and acted, but there are still some pending points to be solved before it can be committed. And I would like to thank Jan and Andrew for all the feedback so far. Do you think there will be any perceivable performance difference in timer delivery latency when CPU pinning is in use? I'm not sure it will be that different in that case. I mean, I think timer delivery, well, virtual timer delivery would be fairly similar. I think, I don't know, maybe we'll get a little bit more of performance by not doing so much logic in the VM entry path, but I'm not sure that would be something that you will notice on using a normal workflow. I mean, if we try to stress the hypervisor to do a lot of VM exit and VM entry, we may see a slight difference, but I'm unsure it will make any difference on real workloads, I think. Does this result in many cases end of interrupts being tracked from guests when they shouldn't be otherwise? Is there much overhead from that? Not really, because we can set which end of interrupts we want to trap. So we can do selective trapping. I mean, well, I think that depends on the hardware support. So either you trap for all the end of interrupts when you don't have hardware support, or you can select which vectors you want to trap for the end of interrupt. So in that sense, it's not shouldn't introduce any more overhead, I think, than what's already there. We already trap for PCA pass-through, so that's going to be fairly similar to that.
But it's still quite a few more EUIs that we trap. It's just that we hope to compensate for that by saving elsewhere.
Yeah. Yeah, I mean, yeah, we have to trap on. Yeah, but it's also the case that in the current logic, we also need to trap for end of interrupts when we have one virtual timer interrupt pending to be injected, because we want to detect when we are capable of injecting that interrupt. So there's also some more, there's already some end of interrupt trapping done by Zen related to virtual timers at the moment. Yeah, I think that's all from me, unless anyone has further questions. I don't think I have anything else to add. Sorry, I think it's been a little bit too technical, but I hope you have been able to follow.
I just wanted to add that the issue became pressing when we started experimenting with K-dump functionality in the guests. So in case of K-dump, you start your second kernel on the vCPU that is not always the vCPU 0, and you immediately get issues with migrating timers from vCPU 0 to the K-dump vCPU.
Yeah, I mean, actually, I mean, when you brought this up, I already had some of these, some of these that was broken, but I've discovered the issue when trying to use the PID on a FreeBSD HVM guest, because FreeBSD will try to inject the PID interrupt to vCPU2 instead of vCPU0. But yeah, from for Zen server, it was noticed when we did when you did the KXIC work. Yeah, sorry, I should have maybe added some kind of diagram to the patch series. I can add some kind of ASCII version of what I have on the slides. It shouldn't be that difficult to convert to something that I can put on the cover letter, maybe, if that's going to be helpful review-wise. Well, yeah, maybe. I mean, it may be helpful to, I don't know, have a comment in the code. I'm not sure it's worth a document, but right now we don't have a lot of structure regarding documents, so I'm not sure I would know exactly where to place this. Yeah, I guess I could create a document for virtual periodic timers, but I don't know. I think it would be quite empty. Okay, so if there are no further questions, I'm gonna close now. Feel free to catch with me on other sessions or on the hallway tracks. And thank you for listening.
Yeah, and thanks for the talk.
Thank you for all the review, Jan. I know it's probably quite hard to understand what's going on. I mean, I had a hard time figuring out what the virtual timers were doing.
Yeah, it's a big mess that you've taken on to work on. So I really appreciate. Finally, there is someone who hopefully halfway understands what is going on there.
I thought that was you, Jan.
Not really. Tiny parts of it, maybe, but
Yeah, I mean, I think that system probably was designed for a single vCPU or something like that, because, yeah, I'm not sure it doesn't work properly at all. I mean, the logic there, it seems to be designed for a single vCPU system, I think, and then try to scale for multiple vCPUs, but of course it wasn't done properly, I think.
yeah. That's what I think it was. It was first for single vCPU, then
Yeah.
it was living with the assumption that everyone has timers only run on CPU 0. And
Yeah, and then there's also the logic to tie the interrupts to the PID, which is, I don't know, it's all very weird in general, I think.
yeah. Anyway, as said, thanks for taking on all this work.
Thank you for reviewing. Okay, thank you for listening. Bye.